Hello, this is lecture 11 for thermodynamics, and today we're going to do something slightly different with the notes. I've written them out ahead of time and I've scanned them, so that means basically I won't be stopping as much. But what I would recommend that you do is, as you're watching this, hit pause so that you can keep up and actually get this properly into your notes. Right. So let's get started then. First thing, as you can see from the top of my page, we have a midterm. So there's a midterm coming up in this class, and it will be held the week after spring break. It's going to be an in-class midterm. It will take you an hour and a half to complete it, and it is going to be on everything up to what is covered before the break, but it won't cover the material that I'll present on the Monday preceding. So make sure that you use your time wisely, and make sure that you also make use of office hours beforehand too. I'm of course available at the normal times, but if you'd like to set an appointment with me, of course you can do that as well. So there we go. Okay. Right. So last lecture, we what did we do? We quantified what the entropy of mixing was for an ideal gas. So you'll recall earlier in the course, we looked at two sets of particles, red particles and blue particles. And through counting, it became clear that there are many, many, many more configurations, so arrangement of particles, that one would consider mixed than there are that one would consider unmixed. And if you accept the idea that as nature evolves through time, there's equal probability of exploring each and every one of these configurations, then that means just through counting alone, one should find yourself in a mixed state with a much more higher probability than an unmixed state. But at that point, excuse me, we didn't give any numbers associated with these things, right? It was a qualitative picture, and so then I rebuilt it. This idea of mixing within classical thermodynamics. And in statistical mechanics, which you will take later in your careers, you will find the way to go from that sort of counting method that I showed you with the particles into something that's compatible with the functions type approach that we're using in classical thermodynamics. And we also talked about a couple different experiments and basically how things would behave as a function of temperature. Okay, so we ended our discussion with speaking about black body radiation, and today I'm going to be talking in detail about that, and in particular, we're going to look at the fundamental relation of the black body radiator. So you'll recall from modern physics and probably other points in life that, or other courses rather, that when things get hot, and by things I mean everything, they glow. And this includes me, you. It includes the laptop that's sitting in front of you, and it includes the universe itself, right? So at some point you've seen a picture of what the cosmic microwave background is, and if you haven't, I can I'll show you that later on today. But a general property of matter is that upon heating, there's emission of light. So we want to explore this a little bit. Okay, so what exactly is a black body radiator? A black body radiator is an idealized model of a process where light from an object is coming purely from thermal excitations and not in any way due to reflections. So what do I mean by that? If I were standing in front of you right now, even though I'm emitting some amount of light due to the fact that I'm warm, most of the light that's actually coming off my body is reflected from my surroundings. And so we use this concept of a black body radiator to remove any notion of this sort of reflected light that's not in thermal equilibrium. And so this is sort of a thought experiment that you can do. So imagine that you have some sort of material here. So I'm drawing the walls of a material. And there's the small opening, right? This is the small opening. Any light, photons that come into this opening, what are they going to do? They're going to bounce around, right? Being emitted and absorbed and re-emitted many, many, many times. So here I'm showing you one possible trajectory. And this could be a single photon that is sort of reflecting around, or in fact, it could be something where you've gone through several electronic excitations. The point being that light that goes through the opening has a fair amount of time to interact with its surroundings before it bounces back out. So photons that are leaving through this small opening here are in thermal equilibrium with the cavity. This is an example of a black body radiator, a source where photons are in thermal equilibrium with the cavity. Now, why do we sort of make this point? Because we want to talk only not about the light, not about all light that comes from an object, but the light that is in thermal equilibrium with the cavity. As you may recall, thermodynamics is about thermal equilibrium, and so it might not surprise you, or maybe it does surprise you, that thermodynamics has something intelligent to say about this process. So what kind of light comes out from one of these cavities? I just want to actually make sure that things are recording properly here. I always have this this fear that somehow, oh, we look good. I'm going to be talking for an hour and 20 minutes only to find out that my microphone was off. But everything looks good so far. All right. So what kind of light comes out? Well, the type of light that comes out, as I showed you briefly in class, looks like this. So here what I'm measuring is the intensity of light as a function of the wavelength. So over here on the far right-hand side, this is the long wavelength limit, which means low energy photons. And over here is the short wavelength limit, which means high energy photons. And these curves gives me an indication of how much light at each particular wavelength should I expect to be coming out of this opening. And I've noted here, right, that there are, so for a particular temperature, so this corresponds to a temperature, and then this other curve corresponds to a temperature. For each one of these things, there's sort of two very obvious properties that I notice. So one of them is there is some theta max where this function takes a maximum. And as I increase the temperature, so this lower curve here is hot, whereas this upper curve is hotter, or hottest, I guess, in this case. The position of theta max goes to shorter wavelengths. So in this curve, most of the light is coming from this wavelength. And as I increase the temperature of the object, what I find is that most of the light is now coming from a shorter wavelength, and so a higher energy photon. The other thing that I observe from these curves is that as the temperature of the system increases, right, so from this curve onto this curve here, the total area increases as well, as does the peak height here. So this is shifted to the left, higher peak, and the total area of the curve is higher. And if you were to integrate under this curve and sum the intensity, then you will get an expression that will be related to the total power. So this should, if assuming that you have intensity per unit time. So the total power from emanating from this thing is just the integral of I of lambda d lambda. More area under a curve means that the curve is brighter. Okay. So let's look at what the details of the thermodynamics of this are. And if you are interested in seeing where this is coming from in your text, so Colin has a nice treatment of this particular system in section 3.6. And this, I guess, is page 2. Thermodynamics is, at its core, a an experimental science, right? So we have this nice infrastructure that we can use, but fundamentally, we need to input some information into it, right? We can't derive everything from first principles. And so one can either use some experimental data or another theory, for instance, quantum mechanics, as the input to thermodynamics. And then you can sort of, you can make the predictions, which we've already done in class. But ultimately, you need some sort of idea of what's going on in terms of the property of your system. So i.e. how one parameter depends on another. And for the particular case of a black body spectrum, it was noted by Stefan in 1879 that the energy of a black body radiator went as some constant b times the volume of t to the fourth. All right, so this is something that you can sort of measure, fine, in terms of your system. And then the other thing that was noted was an expression for the pressure. All right, so P is equal to U over 3V. Now this one is less obvious. Where do you get this information from? Even conceptually, it's how we've talked about pressure up to this point as a force per unit area. It's difficult to even think. So what does the pressure for a black body radiator mean? And as you can see that I'm noting here, this is actually the more general idea for a pressure, which is that it's a radiation or energy density, right? So if you think about what the units are for energy, so energy per unit volume, this reduces to force per unit area. To get this expression, you need to look at Maxwell's equations. And Maxwell's equations are, of course, a set of classical equations that describe electromagnetic radiation. And if you look at the energy density of an electromagnetic wave, you can derive this result directly. Now, this is sort of beyond this course at this point, so we're just going to have to accept that this relation is true. Now, I'm saying it's a more generalized version of a pressure, but it really is a pressure in the sense that you're used to thinking about. And actually, you can associate a pressure with the light that is coming from the sun. So let's find out how much, what pressure that really works out to. Excuse me. Well, I know that the solar flux, so the light hitting the sun, is about 1.4 kilowatts per meter squared. So obviously this is an important number for something like a solar cell.
Stand up.
And if I use this expression, if I use rather this input into the above expression, and I say how much pressure is the sun exerting on some patch of Earth per unit area, it comes out to 10 to the negative 5 pascals, which is works out rather to about 10 to the negative 10 atmosphere. Which, to just give you a sense of how much that 10 to the negative 10 is, this is about 1,000,000 times less than the pressure due to a sound wave. So very, very little. The solar pressure acting on the Earth is undetectable relative to other fluctuations and sources of pushes or pulls. Okay. Now, before I sort of carry on here, I want to make a point, though. This is really the first time that in our discussion of pressure that we've really used this idea of an energy density, so energy per unit volume, as a way of thinking about pressure. I mean, up to this point, we've sort of talked about it as being a derivative, so in principle, you could see it there. But for the most part, we've sort of been thinking about pressure in sort of the standard Newtonian way, which is, force per unit area. But thinking of pressure as an energy density is useful once we start to talk about thermodynamic potentials, which we'll be doing more of in the latter part of the course. And you can actually just see it from unit analysis, right? So in one of the previous lectures, I showed you the Euler relation, and you'll recall that the Euler relation said that the internal energy U is equal to temperature multiplied by entropy minus pressure volume plus the chemical potential times the number of moles. This guy here, this U, has units of energy, so joules. And if you look at this second term here, I know that the units of volume are meters cubed. Therefore, in order to be able to sum these quantities, the units must be consistent with one another, right? So that means that pressure must have units of joules per meter cubed, right? And you can make a similar argument for entropy, right? I know that the units for Kelvin, or for temperature rather, are Kelvin. Therefore, in order to have the units work out, that means that entropy must have units of joules per Kelvin. This kind of unit analysis is actually is quite useful in terms of A, obviously checking your work, and then B, sort of thinking about these things a little bit more physically, right? Pressure is the amount of energy that you have per unit volume. That's what pressure is. It's not just sort of the force per unit area. It works out to that, but that's not that's probably not the best way to think about it. So think of pressure as energy per unit volume. Now, I guess if you don't really believe that there's energy associated, like, you know, if you're not used to thinking about there's energy in a volume when you have an electromagnetic wave passing through, then one can imagine sort of doing a very simple and dangerous experiment, which is, you know, stick your head in a microwave, which obviously I do not recommend that you do. But believe me when I say that when you have light passing through a volume, there is a lot of energy in there, which can potentially cause problems for you. Okay, so let's go back to our derivation. So I have these two expressions for the black body radiator, and they are that the internal energy is equal to some constant multiplied by the volume times temperature to the fourth power. And I have another expression which says that the pressure of a black body radiator, in this sort of new way that we're thinking about it, is equal to the internal energy divided by 3 times the volume. Now, since I have some expression for U and I have an expression for P, I would, to me, looking at this, if I'm sort of trying to do something with this, this sort of cries out the entropy representation for me. And the reason for that is that sort of by inspection, I can see, right, if I have, if I want to get the fundamental relation for this system, which is what I'm trying to get, right? So I either want U as a function of S, V, and N, or I want S as a function of U, V, and N, then I'm going to have to use these things in front of me. And I know that the entropy representation, if I use the Euler expression, looks something like this, right? So this is Euler without any mole number, right? So we're going to we'll calculate this. I mean, there's no moles associated with the black body radiator, right? Everything is encapsulated by the expressions that I have above, so I can just use this as my expression for the entropy. And this looks like a good starting point, because if I put in my U from above, so if I put this U into this expression down here, then I'll have something in terms of T's, and then I can sort of work this around, and I will be able to get a nice expression. So let's see how that plays out. So the first thing that I want to do is I want to take this expression and I want to put it into 1 over t, right? Because my objective is to get rid of the t's and get rid of the p's so that I'm left with u as a function of s and v. So what I'm going to do is I'm going to solve this equation here for 1 over t, and I can do that just by a little bit of algebra. And then similarly, I want to find some sort of expression for p over t that gets rid of the p's and the t's. And I can do that through substitution of this u into here, and then that will leave me in a good spot. Okay, so I'm going to write out an expression now based on the above. P over t is equal to 1/3 b to the quarter, u over v to the 3/4. And I actually, my 1 over t looks very similar, except rather than u over v, here I have v over u to the 1/4. If I take this expression and this expression and then substitute it in to the Euler relation above, then I can get an expression S, which is equal to 4/3 b to the quarter, u to the 3/4, v to the 1/4, which is, as I've written here, the fundamental relation of an electromagnetic cavity. As I've stated numerous times in the course, once you have the fundamental relation for a system, you know everything thermodynamically about it, and so you can make predictions for things like this. You can make predictions for other thermodynamic quantities. So let's just give you an example of what I can do with this. I'm going to take my fundamental relation, and I'm going to use my expression for U and put it in so that I can get entropy as a function of temperature, right? So I take this guy, I substitute it in. So I have now S is equal to 4/3 b v t to the third. So I can calculate the entropy of this. And let's recall what our expression for heat capacity is at constant pressure. Heat capacity is equal to temperature multiplied by di-S by di-T at constant P, which then means that Cp is equal to bVT to the third. So this is the heat capacity of a black body radiator, which tells you how much energy you need to put into this thing to get the temperature to go up. And you can imagine calculating any other number of thermodynamic observables from this guy. Okay. We're going to look now at a different sort of application area of thermodynamics. And I'm going to be, I guess, going backwards a little bit in terms of what chapter I'm in. So Callan, this is sort of covered in Callan 2.9. Up to this point in the course, we haven't really done a lot with chemistry, right? With the general assumption has been that the mole numbers in our system are either constant or, in the example of the red and the blue particles, we haven't been able to swap between the two of them, right? So we've had different types of materials, but we haven't had materials that are swapping from one to the other. And we also looked at permeable and impermeable walls. And permeable and impermeable walls were able to restrict the flows of particles, but ultimately the total numbers of A and B did not change. As you can see from the title here, our chemistry friends might not be thrilled with this because, of course, in chemistry, things can change from one material to another all the time, right? So let's take something that's sort of familiar. We'll say water. And I want to look at the formation and the dissociation of water from the point of view of thermodynamics. As you know, if I take 2 moles of hydrogen gas and I add it to 2 moles of oxygen, if I provide enough oomph in the form of something like a spark or just by warming it, I can convert this into I should turn off my notifications here. I can turn off, or rather I can convert my hydrogen and oxygen into water. And this can happen pretty violently, right? So just to give you students like videos, let's go to YouTube. I will show you what that looks like. See if we can get this to work. This is
did mature.
All right, I guess we don't want blood. What's going on here? Not a PS4 video game. No, skip that. Here we go. All right. here's the impressive part here.
Firing James is armed.
We'll wait for it.
Suppression water system activated.
Now, I don't know if you can hear the sound or not.
10, 9,
Here we go.
8,
7, 6, 5, 4. There we go.
2, 1, 0, and liftoff of Space Shuttle.
Right.
Plans.
So this is what it looks like
Resupply.
when hydrogen and oxygen
International Space Station.
come together quickly. What you're looking at here, everything that's falling along here. So this is obviously quite hot. And all the stuff that's coming out from the back, this is all steam. So clearly there's a fair amount of energy that comes out from this thing. So you produce water and a fair amount of energy. And in that the preceding little video that I did for you there, clearly we're going from hydrogen and oxygen gas into water. But in this little thing that I have here, I have the arrows going both ways, right? I say that, okay, you can go this way or you can go back there. The arrows here are actually quite important. And the reason that they're quite important is because earlier someone asked a question about whether or not things can go backwards in thermodynamics, right? Like what does it mean to be at equilibrium? And at equilibrium, things don't just stop. You're not frozen in time. But at equilibrium, the rate of a forward process is equal to the rate of a backward process. So macroscopically, it looks like nothing is changing, but microscopically, atomistically, everything is changing. Another way of saying that is that at equilibrium, there is still dissociation and formation taking place, but the rates are equal. I want to understand this issue in terms of thermodynamics. I'm going to take this equation here, and I want to rewrite it just by moving everything over to the right-hand side. So I still have my forward and backward arrow, but now I have minus 2H2 minus O2 plus 2H2O. And rather than write them out like this, I want to switch to a different notation where I can write it as a summation from I equals 1 to 3, where the summation runs over the different types of materials or molecules that I'm talking about. So if I write it in this notation, this new I, these are the values of -2, -1, and 2, which are the stoichiometric coefficients. And then the AIs here, these are the molecule types that I'm talking about in my system. Right? So H2, O2, and H2O. Now, in a chemical reaction, there is a change in mole numbers. This means that the entropy this is going to be a term that matters in terms of the entropy, right? Mole numbers are certainly not fixed. And so the change in entropy, as you will recall, with respect to the change in mole numbers, is equal to a sum over the different chemical components multiplied by mu I, which is the chemical potential of the ith component, over T times dNi, where the R here are the R components. And you had a question in your assignment where you were sort of manipulating a similar expression like this. Okay. I'm going to rewrite this now in terms, this dNi, in terms of these stoichiometric coefficients, which I will do in the following way. Because I want to get this this new into this expression. So this is just in terms of the different mole numbers, but obviously it matters what the relative fractions are. And so now I can put in this different n hat here, which gives me an expression for the change in entropy that looks like this. Okay. Now, I know that at equilibrium, entropy will be maximized when all internal constraints have been removed. and the system is isolated from the rest of the universe. So let's suppose that I have a box, and inside my box, I'm starting off with some hydrogen and some oxygen. And I let this system evolve through time until at some point it has reached chemical equilibrium. At chemical equilibrium, or equilibrium for the whole system, ds must equal 0. So then this implies that this summation over nu I, mu I must equal 0. From water, if I take water, this reads like this. So I have 2 mu of H2O plus mu of O2 plus 2 mu of H2 minus E dissociation. And at this point, you might say, where on earth did this come from? Right? I haven't seen this at this point. Where did this come from? And the answer is I cheated. All right. If I go back to the previous page here, right, I said, you know, we go from hydrogen plus oxygen turns into water. And in words, I said, oh, there's some sort of oomph, a spark to get the whole thing going. But really what there is no, there's some dissociation energy associated with this process. And if there wasn't, if this term wasn't in here, you know, the rocket wouldn't take off, right? Or seen the other way, if I take water and I split it into hydrogen and oxygen, I have to input energy into that system. And the reason that I know that you have to input energy into that system is because, you know, electrolysis requires a battery, right? Thermal dissociation, you have to heat the water up. And when you do a rocket launch, it goes in the other direction, right? So when I go in the opposite direction, energy is released. And this is actually the principle for fuel cells, as I've already showed you, liquid rocket propellant, and so on. Okay, so fine. We know that to split water, I have to put energy in. And then I know that when I go in the opposite direction, this energy is released. The question is, how do I get this number? I know that there is a number, but what is it that I need to do to actually figure out what this number is? And again, as I said to you, thermodynamics is not a theory where you can derive such a thing from first principles. And so I either need to make a measurement of it with, say, light, so I could shine some light on something and initiate a photo-induced excitation. Maybe I could run some current through it. I could heat the system up. Or, you know, shock it. There's lots of ways that you can dissociate water. One should, of course, be careful. You know, depending on what you do, so light, current, or whatever, you might overestimate the energy barrier for a particular process because, you know, maybe you go through some sort of long and expensive energetic process to achieve something, and there's lots of lost pathways that you haven't accounted for. So these experiments won't necessarily agree with how much work that you have to do on the system because, you know, the details matter. But in principle, if you've accounted for all the work and the heat, you should be able to come up with a final point, which gives you the relative energy of the beginning and the final point that you can use in your theory. Okay. Another thing that you can do is you can calculate these things, right? Using, like I said, a higher theory, like the type of work actually that we do in my lab. So just to give you a nice little pitch, so if you haven't seen it already, this is the research that I'm doing. So it's called the CLEAN, Computational Laboratory for Energy and Nanoscience. And calculations on things like water splitting is actually something that we do. So, you know, this is me, this is Graham, this is water, and we're trying to figure out how to do water splitting. And the way that we do it is we basically we simulate water next to something like a metal electrode, right? So here's a paper that I have written recently on this particular problem. And here what we're trying to do, or here what I was trying to do, was start to address this problem of how much energy do you need to put into water in order to split it, right? So this is a plot of water next to a platinum surface, and I'm doing quantum mechanics calculations where one of the things that I'm trying to figure out is that dissociation energy. And if you know anything about platinum, you'll know that actually platinum rather, is a very efficient catalyst for water splitting, and we're trying to find alternative ones that are, affordable. Okay. There's also a website that I'm going to be posting to Blackboard once I finish this lecture, and that on that website, if you're interested, you can sort of play around and look through different calculations that have already been done on materials such as water and that, where people have used quantum mechanics to compute the various dissociation energies and the barriers to different chemical reactions. All right, now we're going to go back to the problem at hand, and I want to make an approximation so that we can sort of solve this thing analytically, which is I'm going to make an approximation that all the species are quasi-ideal. Now, what do I mean by quasi-ideal? Quasi-ideal in this case means that their equation of state are given with C is equal to 5/2. So the C from the ideal gas law, you recall, right? So we've already said U is equal to 3/2 nRT for a monatomic ideal gas. And for a diatomic ideal gas, we put a factor of 5/2 in there. So we're going to say that they're ideal, but through the addition or removal of energy, I can convert from one form to the other, right? So I have an ideal gas, I add energy, and then I can turn it into a different type of material. This is a rough approximation of what happens in real life. I mean, in practice, you don't actually do this because in terms of chemical accuracy, it's not going to give you the type of details that you need. But it's instructive for the purposes of talking, because it lets me connect this term mu rather in terms of the pressure and temperature straightforwardly. Okay, so if I do this, then I can write that mu sub I, so the chemical potential of the ith component, is equal to RT times ln P plus ln x sub I of phi I of T. And I'll explain which each one of these are in turn. So the first one should be self-explanatory. So this is the pressure of the container. This is the pressure of the box that I'm giving. The second term, this ln xi, this is the ratio of the mole number of the ith component divided by the total mole number of the system. And then right, so in this case there are 3 of them, so this would be the total moles in the system. And the phi I that I have here is just some arbitrary function that comes from integration. It's a constant of temperature and pressure, and it basically doesn't matter for what we're going to be doing, but in principle it's there. From before, I had that a sum over nu I multiplied by mu I is equal to 0. This is true at equilibrium. So then that means that I can write out the following, which is the sum over the I components, mu I ln x sub I, is equal to negative sum over I mu I ln P minus the sum over I nu I phi I of T minus this dissociation energy divided by RT. Okay. I can now rewrite, so I'm going to bring this nu up into the power here, and I can rewrite this expression to give something like this. And now if I exponentiate everything, remember that these things are all sums, I'm going to get something that looks like this. So I have e to the ln of, and I'll just show you what the individual components look. So say x sub 1, nu 1, plus ln x2, nu 2, plus, and so on, is equal to, and then I'll exponentiate everything on the right-hand side, which is ln of p to the negative nu 1, plus ln of p to the negative nu 2, and so on, And then I also have minus this sum that runs over this constant, e to the negative dissociation divided by RT. E to the ln to this sum here, if you remember your exponential rules, I can divide this up like this, and I'm only showing two terms here, but of course there's multiple other terms, is the same thing as this following line here, where I've written out each one of these exponentials like this, and I'm writing down each one of the exponentials like this. And over here, this kt is just this whole thing, e to the whatever of this whole thing, right? So some number times t. I need a insert dot, dot, dot here, and a dot, dot, dot right there. I forgot my dots. Is there a way I can draw dots? Let's find out if I know how to draw dots. Dot. That doesn't look like a dot. Let's see. Dot. That doesn't look like a dot at all. All right. Well, that vaguely looks like a dot. How do I make this a dot? Can I make it a dot? Oh, I even have a line style called dots. Let's see how that. Well, those are too big a dot. Wait for it. There. Oh, here we go. Look at that. Use of technology, 5 out of 5. There you go. Dot, 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 dot. Excellent. Right. This has a very clean form here, right? For a few reasons. So number one, as you can probably guess, this exponent is going to knock off the ln function here, and I'm going to drop back to this. Okay, so that's fine. And in fact, I can bring, before I do that, I can bring the new outside. We'll hold off on that for a second. But I can also sort of write it a bit more cleanly. So this, what am I trying to say here? This you have seen before, right? This is called sigma notation. And in sigma notation, each one of these elements, when you expand it, gets summed like this, right? There's another type of expression that you can use, which is you can form something called a pi product, right? So I'll just write it out here. This is called a pi product. And the way that a pi product works is it's just like using sigma, except that rather than putting plus signs between each one of the terms as you expand it, you put multiplication. So it's sort of a cleaner way to write this thing down, and this is typically how people do it. So I have the pi product of these terms is equal to pressure to the power of this sum over the coefficient multiplied by k of t. This thing has a particular name, which is called the law of mass action. And I can, this kt, if I solve for it, it looks like this. And what this thing does is it gives you the equilibrium rate constant, so like the Arrhenius constants that you would observe at equilibrium, okay? That we can see between these different types of, how shall I say it, species, right? Okay, so I want to take a minute to sort of show you what you can do with the law of mass action. So how does it work in practice? Remember, this derivation was based on sort of a very idealistic form of the different materials that we're talking about. If I do a little bit, just for instructive purposes, if I do a more realistic version of the law of mass action for a real material, like say hydrogen gas, then, which I'm not going to derive for you now, but you get an expression that looks sort of like this. Well, it doesn't look sort of like this. It looks exactly like this. So this is the law of mass action for molecular hydrogen. And the reason that I want to show you this is because there's a sort of an important consequence that will become clear in a moment. So first off, so what are these things? Okay, so the x's here are the mole fraction of hydrogen, all right? The Ma is the atomic mass of hydrogen. Ga and Gm are atomic and molecular degeneracy. It's just how many different states you have that have the same energy. And then the theta R and the theta V, these are these rotational and vibrational temperatures that I've talked about previously, right? So theta R is the Boltzmann constant times T, if I convert the rotational energy, so the lowest rotational state, eigenstate of a hydrogen molecule into temperature, that's what theta R is. And then similarly speaking, if I convert the lowest vibrational state of a hydrogen molecule to temperature, this is what theta R is, right? So it's a characteristic temperature scale for those fundamental excitations within hydrogen. This looks like a beast, right? It turns out that it's not that bad. If you numerically, if you put sort of these numbers in, and then you numerically solve this thing, you can actually plot out the mole fraction of hydrogen as a function of temperature and pressure. And this is what I'm going to do right now. So on the y-axis here, I'm plotting mole fraction of hydrogen. And then on the x-axis, I'm plotting the temperature. And for the moment, I want you to focus on this curve here, which I'm going to show here. So at low temperature and low pressure, so the pressure here is, what is this? 0.0001 atmospheres. At low temperature and low pressure, the mole fraction of atomic hydrogen is 0. All right, what does that mean? That means at low temperature and low pressure, low temperature and low pressure, obviously, you know, relative to these energy scales that I'm talking about up here, the mole fraction of atomic hydrogen is 0, which means if you have hydrogen or hydrogen gas in front of you, all of it will be in the form of H2. Right. If I take that H2 gas, which we're used to thinking about, and I heat it, and I say, let's go to 1,000 Kelvin, what fraction of molecules have dissociated? The answer is 0. Everything is still in molecular form. As I heat this system, at some point, say around 1,500 or 1,700 Kelvin, I start to find that the system is partially dissociated. So we'll say 1 in 100 molecules have split in half, and now I have some individual atoms that are bouncing around that have dissociated. As I continue to heat the system and the temperature goes up, what I notice is that more and more of the molecules in my system have broken apart, right, which is a form of chemical reaction. And so I reach a point around, say, 2,000 Kelvin, where half of the molecules have broken, or I guess it would be a quarter. It depends on how you want to do your math here, but or a third, and I'm not going to do that in my head, but we'll say some of them have broken. And as I can, so I have a mixture at equilibrium between hydrogen and atomic, or hydrogen gas and atomic hydrogen. So I have an equilibrium number, or an equilibrium mixture rather. And as I continue to heat the system, eventually I get to the point where everything is dissociated and I only have atomic hydrogen, right? And as I heat the system more, nothing happens with respect to this chemistry. I mean, don't get me wrong, as you heat hydrogen more and more and more, totally cool stuff happens, right? You form a plasma. If you get high enough temperature, the whole thing will eventually, you know, form a star. So that's cool. But with respect to the chemistry, you know, of dissociation, that's pretty much over. So that was at 0.0001 atmosphere. Let's say that I do the same experiment, but now I do it at 0.01 atmospheres. So I start, the system is fully molecular. I heat the system. Now you'll notice that I have to go a little bit hotter before I start to dissociate. And this midpoint here has also translated to higher temperatures, right? The story is basically the same, that as I get to higher and higher temperatures, eventually it flatlines. But as I increase the pressure on the system, so this line right here is 1 atmosphere of pressure. As I increase the pressure of the system, hydrogen molecules survive to higher and higher temperatures, right? Because this midpoint here is around, what is that? Say 3,500 Kelvin, whereas the midpoint at lower pressure was around 2,000 Kelvin. I want to think about this, a couple of these things in some detail. So let's make some comments. So the first comment that I have is that the dissociation energy of hydrogen, the work you have to do to turn a hydrogen molecule into two atoms, hydrogen gas, is 4.53 electron volts. All right. So let's look at what that actually means if I were to draw it out. So this is an expression for, actually this, I just noticed the typo here. This should not be a U here. This should be a V. Let's see if we can figure out how to, oh, this is totally going to be 5 out of 5 here. Can I do a V? No, I've highlighted everything. All right. Let's see if this is going to work. Can you? No, that's not a thing I can do, apparently. Wait. How does this work? All right, we're going to go old school on this thing. By old school, I mean this isn't going to work at all. Ah. Oh, I have to click on this thing. This must be so painful for other people to watch. Here we go. There's nothing more aggravating than watching someone else use a computer. What is going on here? Wait. Well, that didn't really turn out how I thought it. Oh, you know why that's like that? Ah, V. I like that V. V for victory. Oh, dear. Ah. Like I said, everyone, 5 out of 5. There we go. Wait for it. Oh, that's a little big for a V, I guess. Wait, we're going to remove this. We're going to... There! Nailed it. That's a V. Ha-ha. Okay. The interaction potential between two hydrogen atoms. This is what I'm plotting here. This is this V. As we've discussed before, atoms don't like to be too close. We don't like being close. And if there's some sort of attractive region between them, and it's bound, there's a little well here. And as you get farther apart, there's a pull for these things to come together. And of course, the details of the shape of this well and the depth and so on is due to the nature of the interaction, right? So if you have sort of a van der Waals type interaction, then it tends to be a shallower well and it's a different shape. And if you have a strong covalent interaction, then it seems to be a deep well with a very sharp bend to it. But for now, let's not worry about that. Okay. So generally speaking, you have a well that looks like this. There is some minima, which corresponds to the bottom of the well. And for a harmonic, within a harmonic approximation, this is equal to the equilibrium bond lengths of these things. And there's some sort of depth associated, where the depth is the amount of work that you need to do to pull these two things apart. I said that experimentally and theoretically, you can calculate this number. The work that you have to do is 4.53 eV. Fine, fair enough. My question is, what is this number in terms of temperature? Okay, or better posed, how much? At what point would what amount of kinetic energy, or what temperature rather, would I need to bring a system to sort of expect that the kinetic energy floating around is going to be equal to this amount? Well, I can convert it, right? So kBT, so kB is the Boltzmann constant, T. If I just set that equal to the dissociation temperature, it works out to roughly 52,000 Kelvin. Why am I pointing this out? If I told you that the depth of a well is 4.53 electron volts, and I said, estimate the temperature at which hydrogen dissociates, naively, you might just say, well, it dissociates at 50,000 Kelvin. And I mean, yes, you would be right if I go back to this little thing here, that at 50,000 Kelvin, which is off the screen because it's so far to the right, everything is dissociated. It turns out that it actually, for thermodynamic reasons, i.e. entropy, things dissociate much, much lower temperature. So don't get distracted by this, all right? Because there is full dissociation well before this point. So don't think in terms of a mechanical escape velocity, right? And as I'm noting here, this is a common mistake made by physicists in particular, and mathematicians and engineers and everybody. And at a younger, more naive version of myself, I thought similar things. Okay. And just as an aside here, on Thursday, we're going to be talking a little bit more at velocity distribution. Or sorry, Wednesday. Materials science is on Thursday. Apologies. Okay, so on Wednesday. I mean, you're welcome to come to material science class too. I mean, you need this course as a prerequisite, and you also have to have other courses, but I'm sure it'll be fine. Okay, so what's another observation? The next observation that I want to make on this guy here, and I apologize for the back and forth here, but I guess we're just going to have to make do. I notice that as I increase the temperature, right, this midpoint is going to the right, okay? Which means that in words, as you increase the pressure, the dissociation, the temperature that you need to get to dissociate increases, right? So as I go from 0.0001 atmosphere, the temperature required to reach 0.5 goes up from about 2,000 Kelvin to 3,500 Kelvin. And if you focus on that midpoint and you just solve this system numerically, what you will find is that you get a curve that kind of looks like this. So I'm plotting pressure here, and this is temperature, and it looks like it goes up. And so you might think that in the limit of very, very high pressure, right, so way up here, the temperature required to dissociate hydrogen is actually gets higher and higher and higher. But it turns out that this is not the case, okay? And I can convince you of this with a, let's see here. We can find it. As you may know, so let's see, we'll flip back, we can find this. You may or may not know someone who's looked at this problem before. And, oh wait, here we go. Let's see. Back in my younger days, during my PhD, I actually attacked this particular problem, which was calculating the phase diagram for hydrogen as a function of temperature and pressure. So the temperature here is about the ones that, roughly what we've been talking about, from 0 to 5,000 Kelvin. And then the pressure scale, though, here is actually much, 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 much higher, right? So I've been talking atmosphere. So really, we've been buried in this part of the phase diagram over here. But if you pressurize hydrogen, eventually the gas will turn into a liquid. And if you push even harder, you can actually dissociate it. And so one of the things that I did during my PhD was I calculated where this dissociation transition happens. And what you notice about this curve is it has a negative slope, all right? So these calculations, which I'm claiming are somehow correct, would seem to indicate that everything that I've said in the first part of the lecture was wrong, right? Because this is saying that as you increase the pressure on hydrogen, the temperature required to dissociate actually goes down. So my question to you is, which one of us is wrong, right? New me or old me? Negative slope, okay? So don't bother putting that slide in there, but this is worth going in your notes. So which one of us is wrong? Well, the answer is we're both right. Old me and new me are both right. And the reason is because, if I go back a couple pages where I'm writing this dissociation number down, I'm actually just giving it to you. I say, right, it's this number, 5.3 electron volts, but I'm sort of throwing something under the rug. And the thing that I'm throwing under the rug is the fact that, in general, the dissociation energy of a molecule or some sort of structure depends on the density, right? So this curve here is what the interaction between two hydrogen atoms looks like at 0 pressure and 0 temperature. Once you increase the density of a material to a high value, like the type that I'm talking about in this phase diagram here, you get interactions between the different particles, and that will actually start to modify the dissociation energy. And if I flip back to another page here, this is actually something that has also been investigated by someone that you may or may not know. Let's find, right. So you can actually calculate so here I'm changing units. So this is an what is it? Energy times inverse KB over T. Okay, fine. So this is what the hydrogen-hydrogen interaction potential looks like once you go to a relatively high pressure, all right, and a high temperature. So this is at 3000 Kelvin. And as you increase the temperature, you actually find that this interaction potential changes. And as you increase the density, so this is at 10 GPa, right? As you increase the density of your system and go to a higher pressure, 175 GPa, then all of a sudden this interaction potential looks completely different, right? So there's a tiny little minima here, but as you heat through the system, you find that it changes. So, phew, so we're both correct. New me and old me are both right. But just remember that these parameters that I'm giving you here, right? Things like the dissociation energy are not constants, right? They depend on the details. And so don't make the mistake of just saying, right, I can just grind through all possible pressures and all possible temperatures, and that'll give me a result. Because for at least in the case of hydrogen, and I mean, to be honest, every other material, these things change. So the amount of work that you have to do to dissociate something has changed, and it can have very qualitatively important effects on things like the phase diagram, giving you a negative slope. So since it's sort of screaming at us in the face here, hydrogen is also a pretty cool material because, as we'll learn in future in material science, it actually undergoes what's called a metallization transition. So normally hydrogen is an insulator in its molecular form, and it's an insulator in its atomic form too, but at some point it actually turns into a metal. And so metals have, of course, very different electrical properties than insulators do. And some people have actually suggested that if we are ever able, so by some people I mean Neil Ashcroft, have suggested that if we're ever able to find room temperature hydrogen, metallic hydrogen rather, at high pressure, it might actually be a room temperature superconductor. So the field of hydrogen is a hot one, haha, see, because it's hot. And it's one where there's a lot of really interesting science that's going on, and it's very near and dear to my heart. So hydrogen was my first love, I guess you could say. Okay, so this is what I wanted to say today for this lecture, and I will of course be available for office hours, and you have an assignment which is due on, what day is it due? The assignment is due whatever day is it due. I guess it's Wednesday. Does it sound like Wednesday? Yes, assignments are probably due on Wednesday. It's due Wednesday. So I will see you in class. And if you have any questions, please don't hesitate to ask. Okay, cheers.